All right, now we're going to look at example 2. Now what I'm going to do a little differently is I'll just paste my graph, but as you go, as we graph them, I would just do a quick sketch for yourself. So here's the order I typically go in. I'm going to first say, what is our domain? And we get the domain by saying, what's the only thing you cannot do with this in mathematics? Divide by 0. So to get this value, I'm going to say the denominator cannot equal 0. Now how would you solve that? Plus 1. And so what can x not equal? X cannot equal positive 1. So there's my domain. X cannot equal positive 1. What can x equal?
Anything else.
Anything else. So just to make sure that's clear, I'm going to do XER. That means all reals except for 1. Again, if you want to write it out long ways, you can. It would be negative infinity to 1, parentheses, union, 1 to infinity. That means all reals except for the 1. That's what the parentheses means. It does not actually contain 1. I'm going to skip these right here, the review items, and I'm going to go to wholes. So what's a whole? Let me go back to the problem. A whole is if you could cancel a factor in the numerator and denominator. So on this one, I can't cancel it. Students may think, well, can't I cancel those x's?
No.
I'll prove to you we can't. Let's just come up with a, let's just pretend we have a number for x. What's a good number y'all like?
12.
Here, 12. What if we use 12 for x? If I said this is 12 minus 1 like that. Now, without canceling, what would we say this could be simplified to become? 12 minus 11. Well, if I did think I could cancel, we cancel that and maybe say, well, since it's 12 divided by 12, that should be a 1. What's 1 divided by negative 1? Is it 12 over 11? No, that didn't work. Well, what if you say, well, it cancels. Shouldn't it be a 0? Well, what's 0 divided by negative 1? Is it 12 divided by 11?
No.
See how the math doesn't work? You can't cancel terms, is what that's called. You can only cancel if it's a full factor. So since nothing cancels, it's not a whole. A whole comes from a removable discontinuity. We'll remove it if they cancel. So there's not a whole. So if it's not a whole, what is that discontinuity? It's got to be a vertical asymptote. So we have a vertical asymptote at 1. Now a vertical asymptote is not actually a part of the graph. That's why I'm going to say x equals 1. The domain tells you where the graph is. This tells you what's filling the space where it's not. So on our graph, if you go to the x-axis at 1, and I told you earlier I'm going to paste a graph in, this graph would be in here. Maybe I'll start doing it on the next one. Since I'm already this far, I'll draw one more by hand. That would be our vertical asymptote. X equals 1. Now that's not actually part of the graph. That's why we're saying it's equal to it. The actual graph will not equal that spot. Now the next thing I do is I go to horizontal asymptotes. Now this is figured off of the degree. What's the degree of the numerator?
1.
1. What's the degree of the denominator? 1. And so you ask yourself, are these exponents, the degrees, bigger in the numerator, bigger on top? Are they bigger on bottom, or are the exponents the same?
Same.
The same. So the rule, if you look on the cheat sheet, says exponents are the same, DC, divide coefficients. Exponents are the same, divide your coefficients. So the equation will be y equals, how many x to the first do I have in the numerator? 1. And how many x to the first do I have in the denominator? It's just going to be 1 divided by 1. What is 1 divided by 1? 1. So we're going to go to positive 1 on the y-axis, and we're going to add a horizontal asymptote. Right there. That's y equals 1. Now the y-intercept is found by substituting 0 in for every x. So mathematically, the way you would write that is f of 0 would equal, and you substitute a 0 in. 0 divided by 0 minus 1. Which could simplify to be 0 divided by negative 1. And what is 0 divided by negative 1? 0. We have a y-intercept at 0. Let's put that point on there. There's our y-intercept. And finally, the last thing. zeros of the function are determined where the numerator equals 0. So you'd set that and you would solve that. Well, it's already solved for us. What do we get there? X equals 0. So from here we could graph. I have to approach these asymptotes. I know it's going to go through this point at the origin, so this one has to go towards this asymptote. This one is going to come like this. Now, because the powers are odd, it's not actually an odd function. I'll describe that in a second. But because the powers are odd, this will it will reflect across our asymptotes, kind of like reflecting across the origin. It'll reflect this way, and that's because the powers are odd. Now, this is neither even nor odd, though, because it doesn't have perfect symmetry on the origin. Okay, one more time. Range. All reals, not all reals. And all reals except for 1. Good. So all reals except for 1. I'm just going to write the short version this time. All reals except for 1. Does the graph increase anywhere? No. Does it decrease? Always. It's always decreasing. So let's look more in depth at this function. Ruby, how you doing over there? Ruby. All right, let's look at part B here. It says, prove whether the function is continuous. Now, if you're wondering, how do I prove something's continuous? Maybe you've seen this on Delta Math. You're like, how do I do that? For something to be continuous, each one of these values, the 3 limits and the function itself, has to have the exact same answer all the way across. Okay, so I'm going to copy our picture that we just had right here. So if I copy this picture, let's take a look at what we get here. Whoa, that's huge. And after this, I'm going to just start using Inspire. Sorry, I gotta shrink it up quite a bit. Okay, this one. As we approach the x value of 1 from the what does that negative mean? Just before 1, or coming from the left. As we approach x equals 1 from the left side, so this piece, what's happening to the graph? Am I rising, falling, or getting flat? It's falling. And what symbol represents falling? Negative infinity. So let's say this right here is negative infinity. You know how I'm going to do this? I'm going to say that's negative infinity. And I'm going to call this limit 1, and I'll put a 1 down here so you can look back later and realize that limit corresponds there. Now limit 2. This says 1 plus. That means just to the right of 1, or you could think of it as approaching from the right. As the graph gets closer and closer to 1 from the right side, what do? Rise or fall? We rise. What symbol means rise? Infinity. So I'll put a 2 here. Now the third limit compares the first 2. Are these 2 values the same, or are they different? They're different. The third limit says if they're the same, you get an answer. If it's not, then this does not exist. This limit does not exist. DNE. That limit does not exist. Because these are different. And then finally, f of 1. That means where is the graph actually at 1? Where is the blue graph at 1? Is it actually there? Not there at all. This would mean undefined. This would be undefined. Let me change my color. F1 is undefined. That's because it's not there at all. Now, so are these the same? All the way across? Did we get the same value all the way across? No. If even just one of them is different, then it's not continuous. The function f is not continuous. Not continuous at x equals 1 for a variety of reasons. It's because this does not exist, because these aren't equal, because this doesn't equal those. So f is not continuous at x equals 1 for that reason. Now, one more thing before we move on in this example. Describe the end behavior. Let me copy this as it is this time so I don't have to shrink it one more time. We want to describe the end behavior. That means the limits as you go to the left and the right. So let's write, we'll do the one that goes to the right over here. Let's describe the end behavior as x increases without bound, meaning goes to positive infinity. As this graph goes right, what happens to my y values? Do I rise? Do I fall? Or does it get really constant and flat? This, it actually doesn't keep falling. It approaches this asymptote. What's it doing as it gets closer to this asymptote?
Constant.
It's getting really flat. What's the y value it's getting flat with? 1. So it would be approaching 1. Now what's the end behavior over here? As we decrease without bound, as x decreases without bound, meaning as we go to the left, does my graph rise, fall, or get flat?
Fall.
As we go left, the graph gets
Flat.
really flat. What's the y value it's getting flat with? 1. Now that's where the horizontal asymptotes come into help. Here's a typo. I should have said describe the end behavior using its horizontal asymptote. That's all I needed to say, not the vertical. You would just use the horizontal asymptote. And there it is. Yeah. Okay, to save us time today, and so we're not kind of just losing our mind trying to graph some of these. What I'm going to do is we're going to graph it in Inspire, and then I'm going to walk through why the values are as they appear. Okay, so starting on this next example, example 3, we're going to graph this, and then I'm going to show you how we get those values. And I'm going to drop the review stuff. We're just going to look at the domain, holes, vertical asymptote, horizontal, intercept zeros, and limits. Okay, so let's first go graph this. Open up your Inspires. X squared minus 4 divided by x squared minus x minus 6. That's the function f that we're going to graph. Wrong one, Kevin. Inspire. So to get a fraction, you can hit Control Divide, and it'll give you that fraction line. It was x squared minus 4 over, what was it over?
X squared
Minus x
minus
minus 6.
Yes.
Okay, now this is going to be our graph. And so all I'm going to do here is take a picture of this, and then I'm going to bring it over, and we'll kind of work as we go and explain as we go. Don't start drawing this yet, because I want you to have some space to write out the math that occurs. But this will be our graph. I'll go ahead and put this down here. So we'll have it here for a little bit. All right, so as we get started, here's how I would do this problem, just purely using algebra. The first thing I would do is find where my domain does not exist. What is it in math that you're not allowed to do?
Divide by 0.
Divide by 0. So I want to find where the denominator does not equal 0. This is a trinomial. What did we learn back in lesson 1-5 about factoring trinomials? What method do we use? X method. I'm going to try X method. If you remember X method, it's where you put a times c value up top, and the b value down below the x, where a is referring to the number of x squareds, b is the coefficient in front of x, c is the constant. I don't have a number of x squared, so what is my coefficient then? 1, and so 1 times negative 6 is negative 6, and my b value is negative 1. Remember, you're looking for a product of negative 6, a sum of 1. What are the factors of 6? There's 2 and 3, and there's 1 and 6. Which one could combine to give you a 1? 2 and 3. So it's going to be 2 and 3. Now let's think about the negatives. How do I make it be a negative 1? Negative 3. Perfect. So now, from here, what does this mean? And we're going to do this as we go. We will factor it as you split the a term's power, if you remember. So instead of it being x squared, you're going to have 2 different parentheses of x. And it'll have a plus 2 and a minus 3 inside each factor. Like that. X plus 2, x minus 3. Those are my factors for the denominator. So this is not allowed to equal 0. So my domain here, if this cannot equal 0, one more time, this cannot equal 0. What would x have to be here to get a 0, according to the zero product property? A minus 2. So x cannot equal negative 2. Now what about this factor? What can x not equal here? 3. X could not equal negative 2 or positive 3, but it could equal any other real value. Any other real value it could equal, just not those two. Now to find out if this has any holes, we need to factor the numerator. This is a difference of squares. You might remember that shortcut, but I'm going to act like you don't. I would do a times c up here with b. B's missing. So what's b if there is no x term? 0. It's like you have 0 x's. So let me actually make this c more in place here. Put c there. A would be here. So I'm going to do another x method in case you forgot. This is just in case you forgot difference of squares. So 1 times c is negative 4. And b is 0. What are factors of 4? 2 and 2 and 1 and 4. Which one could combine to give you a 0? 2 and 2. To make it be 0, it has to be 2 minus 2, like that. So again, I split my a terms power, and so I have x plus 2 and x minus 2. So how does that help me on holes? I'll show you. A hole is known as a removable discontinuity. That is a, let me just make that note, that is a removable discontinuity. It occurs whenever a factor can be removed from the problem. You see how I just removed that? We will have a removable discontinuity at which x value? At negative 2. So that means on our graph, if you looked over here, we should have had a hole there. Did our Inspire show us a hole? So we're going to add an open circle right there. Let me get my tool so it shows up right. Fill it white with red. There we go. We should have a open circle right there at 2. Now, you're actually going to be responsible for knowing what the y value is. So if you're like, well, how do I find that? Let me tell you. We know the x value is at negative 2. If you're like, what is that y value? Is it 1? It looks like it's close to 1. How you know is you plug in negative 2 to the remaining equation. So just the unsimplified version, it'll be negative 2 minus 2 more divided by negative 2 minus 3. Let's simplify that to figure out what that point is. That would be equal to negative 2 comma. What's negative 2 minus 2 more? Negative 4 divided by what's negative 2 minus 3 more? What's negative 4 divided by negative 5? Can I turn it positive? Yeah, it's 4 over 5. And you could leave it as 4/5, or you could do it as 0.8. Very good. Or negative 2 comma 0.8. That's what that value is right there. That value, that point, is at negative 2 comma 0.8. That's where that would be, that open circle. Okay, so if the whole is this, the factor that cancels, the one that does not cancel, that stays there forever, is your infinite discontinuity, your vertical asymptote. This is known as a infinite discontinuity. Infinite discontinuity. It's the x value, the factor that does not get canceled, which is x equals what value? 3. Say 3. X equals 3. That's it. X equals 3. So I'm going to add that to my graph now. This is the infinite discontinuity at x equals 3. It should look like this right there. From the factor, the denominator that did not get canceled. That one right there. That's where it came from. That is x equals 3. Got it. Now, looking at the exponents, we're going to horizontal asymptotes. You look at your exponents. Are the exponents bigger in the top, bigger on bottom, or are they the same? Exponents are the same. If the exponents are the same, the cheat sheet says exponents are the same, divide your coefficients. Eats DC is what it looks like. Exponents are the same, divide coefficients. It'll be y equals, how many x squares do I have here? 1. And how many x squares do I have here? 1. It's 1 divided by 1. What is 1 divided by 1? 1. We're going to have a horizontal asymptote at y equals 1. There that is. Y equals 1. Say that again. Exponents are the same. Divide coefficients. By the way, those rules is on your very front of your packet. Those acronyms are right here on this cheat sheet. So if you want to look back, exponents are the same. Divide coefficients. Bobo is bigger on bottom. Y equals 0. And if it's bigger on the top, we will not have a horizontal asymptote. It'll be oblique or slanted. Okay? We're not going to get into that for a while, though. All right, let me pick back up where we were. Where were we? Right here. Almost done. Y-intercept. How do you get a y-intercept? Say it again. How do we get a y-intercept? Hey, Ruby, can you take out your headphone for me? You plug in 0. So, thank you, Evelyn. I'm going to ask that again. Class, how do we find the y-intercept?
Plug in 0.
Plug in 0. Moises, how do I find a y-intercept? Plug in 0. Good. Let's plug in 0. I would use the simplified equation here. It'll be easier. Or actually, maybe it won't be. If I use the standard, this one over here, if I plug in 0, what is 0 squared?
0.
0. It just becomes 0 minus 4 over 0 minus 0 minus 6. Maybe it's easier this way. Which equals, all the zeros basically get simplified out of there. What's negative 4 divided by negative 6? 2 over 3, 2/3. That would be this point right there. That point would be 2/3. 0 2/3. That's 2/3 there. And the zeros. You get zeros from any factor in the numerator that's left over. If I solve this, what would I get here? If I said x minus 2 equals 0? 2. We have a 0 to x equals 2. That would be this point right there. That would be 2 comma 0. To finish off what's probably feeling like the longest problem ever. Let's fill in these limits. What happens as, this is telling us x goes what direction if it says negative infinity? Left. As this graph goes left, does it appear to be rising, falling, or getting pretty flat? Flat. What y value is it getting flat next to? 1. Remember, a limit doesn't tell you where the graph is, it tells you where it's going. It's heading towards 1. Now, what's happening as we go to the right? x approaching positive infinity. As this graph heads to the right, does it appear to be rising, falling, or getting really flat and constant? Flat and constant. Now notice I threw in extra limits here because I have two other discontinuities. Let's do this discontinuity at -2. So I'm going to have a -2 minus and a -2 plus. As we approach -2 from the left, usually I say, is it rising, falling, or getting really flat? Well, this one's different. It's coming to a point. What's the y value at that point? 0.8. 0.8, or you could put 4/5 if you prefer. Now, what happens as you come from the right? Is it rising, falling, flat, or I should say, coming to a point? It's coming to a point. What's the y value of that point? 0.8. Now, because these two are the same, because these two are equal, you could write it as one limit. You don't have to use the plus or minus. You could just say x approaching -2 of f of x would equal 0.8. You could just do it one time. You don't have to do the plus and the minus since they're the same. Since they're equal, the limit exists, and it's 0.8. Not to be misunderstood, f -2 would be undefined. F -2 is undefined because we have an open circle there. The graph does not exist at -2, so the function's not defined at -2, but the limits do exist. Okay, and now let's talk about it at 3. Let's go 3 from the left, 3 from the right. What happens as we approach 3 from the left? From the left, as we approach 3. Does the graph rise, fall, or get flat? Falls. Put negative infinity. What happens as we come from the right? Rise, fall, flat. Rise. Are these equal to each other or not equal? Since they're not equal, that means the limit as x goes to 3 does not exist. You would say D and E. Does not exist. Does not exist. Since these two limits are not the same.